The title of the lab project we have chosen to do is the effect of various liquids on the index of refraction. This lab was completed by myself, Nicole Petrason, and Samuel Vargas. To begin, the overall purpose of this lab was to first understand and apply the concept of Snell's law in order to find the angle of refraction for various liquids. The second objective was to compare our expected values of index of refraction to our calculated values to find percent difference. We also wanted to use our results to calculate the speed of light going through a specific medium. There were a couple theories that we used throughout this lab in order to calculate our results. The first would be Snell's law. To determine the index of refraction of a medium by measuring angles of incidence and refraction. The equation, which can be found in the bottom corner, is as follows. N1 equals incident index, N2 equals the refractive index, sine theta 1 equals the incident angle, and sine theta 2 equals the refracted angle. This law allows us to predict the degree of the refraction as light goes from one medium to another. Another theory is that the index of refraction is the ratio between the speed of light in free space and its speed in the medium. Using the information from Snell's law, the speed of light in a particular medium can be found. This equation is N equals C over V. In this equation, N equals the index of refraction, C equals the speed of light in free space measured in meters over second, and V equals the speed of light in a particular medium, also measured in meters over second. As seen in the bottom corner is a graphic that helps to represent some of the theories and methods that we will be doing throughout this lab. It is a great example in order to understand what the overall concept looks like.
The equipment needed to perform this lab procedure are 1 cup of water, 1 cup of witch hazel, 1 cup of vegetable oil, a planar lens, light source, plastic ruler, protractor, and Microsoft Excel. The steps for this lab procedure are as follows. First, obtain a planar lens for the purpose of holding the desired liquids. Then, mark the point on a sheet of paper to indicate where the container will be placed and aligned. Our lab group found it helpful to do a cross shape as it not only marks the point at which we would refract the light, but also indicated what orientation the planar lens would be in by defining the perpendicular axis. Then, place the planar lens with its edge on the point of refraction and shine the light at that point at an angle to the vertical axis. Then, use a pencil to mark the point where the light enters the chamber as well as the point where the light exits the chamber. Finally, draw a line to connect each dot with the center of the cross. Take measurements of the angle from the vertical axis using a protractor and record the data in Excel. Some sources of error from this lab experiment could be from human or systemic error. An example of human error would be if we improperly set up the procedure or if we measured inconsistently. Examples of systemic error would be if the chosen container had curvature in the walls or if the walls were too thick. Particularly with the oil measurement, liquid on the outside of the walls can decrease accuracy of the data. Finally, if any of the tools we used were tampered or faulty, that could have been a source of systemic error.
We then took the values that we had gathered and inserted them into a chart in Excel, recording the angle of incidence, the angle of refraction, and the index of refraction for air. We then used these three values to calculate the index of refraction for the liquid that we were testing. We ran 5 measurements for each liquid and thus calculated 5 indices of refraction for each liquid. We averaged these 5 indices to find an average index of refraction for each liquid, which we used to compare to the expected index of refraction for the liquids. Our expected index of refraction for the liquids that we tested were 1.333 for water, 1.346 for witch hazel, 1.470 for vegetable oil. The average indices of refraction that we calculated and the percent difference for each of the liquids were 1.314 for water at 1.44% difference, 1.334 for witch hazel at 0.93% difference, and 1.430 for vegetable oil at 2.81% difference. We then used these calculated indices of refraction to calculate the speed of light in each of the liquids. The speed of light values were as follows: 2.28 times 10 to the 8th meters per second for water, 2.25 times 10 to the 8th meters per second for witch hazel, 2.10 times 10 to the 8th meters per second for vegetable oil. In conclusion, the data values that we gathered were close to the values that we were expecting, indicating that we had fairly accurate measurements. We also found that the speed of light is inversely proportional to the index of refraction of the medium that the light is traveling through. As such, light travels slower in mediums with a high index of refraction, as opposed to mediums with a lower index of refraction. More accurate measurements might have been achieved with a longer and wider container, because the refracted light would travel further, giving us a more precise angle measurement.